Hello Math 152 students. In this video, we'll take a look at an overview of Chapter 11 and dive into an example from 11.1. Chapter 11 is all about inference on two samples, whereas in Chapters 9 and 10, we were focusing on one sample where we could think about one column of data at a time. There are three different scenarios we'll see and focus on in Chapter 11. The first is proportions. We'll compare proportions from two independent samples. Think about this as we're going to have two p-hats to deal with, and we can compare to one another. Then we'll work on comparing mean difference from a paired or dependent sample, or we could focus on comparing means from two independent samples. So you can see with the vocabulary here, we need to clarify a little bit of what we mean with independent and dependent first before we get into these examples. This first scenario, proportions, will be addressed in 11.1. The paired samples will be 11.2, and the independent samples with means is going to be in 11.3. We will say that a sampling method is independent when the individuals selected for one sample do not dictate which individuals are selected in the second sample. A sampling method is dependent when the individuals selected in one sample are used to determine the individuals to be in the second sample. So this can happen in a variety of different ways. We'll look at some examples and clarify, and then brainstorm some other ways that it can happen. So another way to phrase dependent samples is to refer to them as matched pairs. So dependent samples are often referred to as matched pair samples. It's possible for an individual to be matched against himself or herself, which we'll address after we see some specific examples. In other words, think about matched pairs as pairing up two pieces of data, but the two pieces of data can come from two individuals, or it can be one individual that produces two pieces of data. Okay, so in each of these examples or scenarios, we will determine whether the sampling method is independent or dependent. Let's take a look at this first example. A researcher wants to know whether the price of a one-night stay at a Holiday Inn Express is less than the price of a one-night stay at a Red Roof Inn. She randomly selects 8 towns where the locations of the hotels is close to each other and determines the price of a one-night stay. So in this case, let's compare our two options. Our two options are going to be whether this is an independent sample or a dependent sample. Now, in this case, think about the first set of data and the second. We can think about our first column of data would be our Holiday Inn Express prices, and our second column of data is going to be our Red Roof Inn prices. Notice the way the researcher is selecting. As soon as she picks Holiday Inn, that's going to be in a particular location, and she is going to immediately select a Red Roof Inn in that same location. In other words, she selected the towns and then got prices from each hotel in that particular town. So think about this as paired. She specifically paired them up town by town because perhaps the price of a hotel in Orlando is going to be different than the price of a hotel in Hickory, which is going to be different than in New York City. And these locations are going to give us different prices. So if we were to compare the price of one hotel in New York City to the price of the other hotel in Hickory, we would already have a problem to start with. So pairing up geographic locations and a paired sample done like this makes sense. So we would say that this example is a dependent sampling or a matched pairs case. Let's look at our second one. A researcher wants to know whether the state quarters introduced in 1999 have a mean weight that is different from traditional quarters. He randomly selects 18 state quarters and 16 traditional quarters and compares their weights. In this case, one of the first tip-offs is that we have different sample sizes. We had 18 state quarters and 16 traditional. And there's no indication of any sort of pairing up, but the difference in sample sizes also poses a problem. It's possible that when you're doing independent samples, that you don't have equal sample sizes between the two sets, and that's okay. But that is a tip-off that is independent sampling. In other words, when we picked the first state quarter, that didn't indicate which traditional quarter was paired with it. There's no sort of natural pairing in this case. So this is an example of an independent case. Now, even if we had 16 and 16 or 18 and 18, there still wouldn't have been a pairing. So don't assume that just because you have the same sample size in each set that they're paired. That's not the case. You have to have some way that is specifically paired up or some way of matching one individual to another individual in the two data sets. So just to recap what we've said, the first sampling method is dependent since the 8 Holiday Inn Express hotels can be matched with one of the 8 Red Roof Inn hotels by town. And for the second scenario, the sampling method is independent since the state quarters which were sampled had no bearing on which traditional quarters were sampled. There was just no pairing. All right, so before we do an example, let's just go back to our 3 scenarios really quickly. For proportions, we're going to have independent samples, and the means will have a dependent and an independent case. So our first example here, continuing with 11.1, is going to be about 2 population proportions. And I want to give us a quick overview of our steps, which are going to feel very similar to Chapter 10 steps. We're going to see the exact same 5 steps in hypothesis testing, and then we can go ahead and jump into a specific scenario. So before we give our steps, think about our conditions. In Chapter 10, we had to work on that n times p times 1 minus p condition, and also the 5% in comparing our sample size to our population. We're going to see those again, but we're going to have to verify it for each of our 2 populations. So think about our hypothesis test regarding the difference between 2 population proportions. You almost have double the conditions to check. So jumping into our first point, you do want to make sure your samples are independently obtained using simple random sampling, meaning for our populations, they're not paired up, and then you want to have some indication that random sampling was used. You don't want to do inference or hypothesis test on a convenient sample. That's the same concept that we saw in Chapter 10. If you handpick the data, then trying to test the hypothesis with handpicked data isn't very meaningful. So most of the time, the way our setup is done takes care of our first point. Then our second point, notice I have subscripts. Instead of just n times p times 1 minus p is greater than or equal to 10, here we have our n1 for our sample 1, our p hat 1, which is going to be our population proportion from our first sample, and our p hat 1 here. So that condition has to check, the n times p times 1 minus p for population 1. And then the same n times p times 1 minus p has to check for condition or for sample 2. Then the 5% rule, they've tried to summarize it like this. This is saying our sample from population 1 has to be less than 5% of our population 1, and our sample 2 has to be less than or equal to 5% of our population 2. So this is just the sample size is no more than 5% of the population for each group individually. So then once we verify our conditions, you have to do your setup. Notice for the null hypothesis that the null hypothesis, no matter if you're doing two-tailed, left-tailed, or right-tailed, still has an equals. This is exactly what we saw in Chapter 10. You always start off with assuming equality or nothing is different. So we start off saying, well, if nothing's going on, our 2 groups are going to have similar proportions. But in a two-tailed test, the alternative is not equal, left-tailed less than, and right-tailed is greater than. So once again, we'll read our scenario, and our scenario will indicate which of the 3 types we need to use. Here, we're going to have 2 different subscripts, just like we had in our conditions. So once we do our setup, we'll make sure we have a level of significance or alpha specified. We'll use StatCrunch to compute the test statistic and p-value. Similar to Chapter 10, if our p-value is less than the alpha, we reject our null. And then in Step 5, we want to state our conclusion in everyday language. So let's look at how this plays out. An economist believes that the percentage of urban households with internet access is greater than the percentage of rural households with internet access. He obtains a random sample of 800 urban households and finds that 338 of them have internet access. He obtains a random sample of 750 rural households and finds that 292 of them have internet access. Test the economist's claim at the alpha equals 0.05 level of significance. So after you read a scenario, make sure that you can pick out what data goes with what group. In other words, making sure we don't mix which numbers go with urban and which numbers go with rural as we're doing our calculations is going to be important. Let's go ahead and go through our steps. The first step is to verify that we have all of our requirements, those conditions. So the first thing is the samples are simple random samples that were obtained independently. Here, all they told us was that the researcher obtained a random sample of 800 urban households, and then he obtains a random sample of 750 rural households. There's no indication that these are paired up, so that's the independent samples. And here, they mentioned that these samples were done randomly. We're going to assume those are simple random samples. Then, in our next part, we're subscripting 1 for the urban households. We had 800 total households, 338 with internet access. So think about this as our number of successes and our total. 750 rural, 292 of those were successes with internet access. So our p hat 1 is going to be our proportion with internet access for our urban households, about 42%, 0.422 approximately. And for rural households, about 39%, 0.389 approximately for our proportion. So we will take those two numbers and use them to check our conditions. Here, we don't have any other proportions in the problem, so we're forced to use our p-hats in our condition, kind of like we saw in Chapter 9 with confidence intervals. Just make sure here you're not mixing up what goes where. We'll use all of our information from population 1, our N1, our P1 hat, so in other words, our total population of urban, our proportion of urban, and our 1 minus our proportion of urban to check. Notice we're getting numbers for our N times P times 1 minus P that are much bigger than 10. And then we do the exact same thing for the rural households. So 2 checks, twice the work. And then the third part about the 5%, 800 urban households is definitely less than 5% of all urban households in the US. And then 750 rural, that's definitely less than 5%. So we're good to go. All right, so our next step is to make sure we set up our null and alternative correctly. So our null is going to be, if nothing is going on, the two population proportions are going to be equal. There's no difference. But what the researcher really thinks is that urban households have a greater proportion of internet access than rural. So we're suggesting a P1 is greater than P2. That's our alternative. Another way to state this is we could move the P1 and P2 to the same side and subtract so that you have an equal 0 or a greater than 0. My preference personally when I read a problem is to do the first. And then sometimes, depending on the software that you're using in StatCrunch, it'll have a preference. So if you see this second scenario, you can always move it back and make it look like our first scenario. They're identical. Then in step 2, we'll make sure we specify our alpha. Our problem gave us the alpha of 0.05. So step 3 is going to be to find our test statistic and p-value and use StatCrunch to do this. I'm actually going to pause this video. We're almost out of time for our 15-minute time limit, and we'll pick up with StatCrunch in the next part.